So continuing with the theme of gratuitous violence in physics, we're moving from projectile motion into collisions. So in order to talk about the physics of two objects slamming into each other, we have to introduce a new quantity called momentum. So momentum, this one here, is represented obviously by a p. And because it's a vector, we're going to put the vector symbol on top of it. That means that not only do we have to worry about how big the number is, we also have to worry about which direction it's pointed. So the way you calculate momentum is you take the mass of the object and you multiply it by the velocity vector. So in order to get this number, I need to know how heavy a thing is and how fast it's going and where that velocity is pointed. So if I were to give you an example, let's make a thing called Kelly, just so we don't have to keep saying the mass over and over again. Kelly is going to be 15 kilograms. All right, so we are going to let Kelly travel this way at 4 meters per second. So that's a speed, but I need a velocity. I need this as a vector. So I need some way of writing which direction precisely this is headed. So I'm going to add a little detail here that Kelly is headed 30 degrees down from horizontal. Okay. So the first thing we have to work out here is the velocity vector. So Kelly has a velocity that's a little bit to the right and a little bit downwards. So that's velocity in the x direction, that's velocity in the y direction. Now this is very similar to doing the muzzle velocity from the cannon. I just need to break this hypotenuse into the legs of a right angled triangle. So looking at this arrangement, the 4 meters per second then is the length of the hypotenuse. So if I go to work out the Vx and the Vy, Vx is adjacent to the 30 degrees. So cosine of 30 will be Vx over 4. Therefore Vx is 4 cos 30. And the Vy is opposite of the 30-degree angles, so that's a sine ratio. Sine of 30 would be Vy over 4. Therefore, Vy is 4 sine 30. I'm going to actually render these down as decimals, just because I can, and it will be a little bit less confusing. So, we've got to get this thing in degrees, which is annoying. So cosine of 30 is 0.8660 multiplied by 4 gives me 3.464. And I believe sine 30 is 0.5, so let me confirm that. Sine of 30 is 0.5 multiplied by 4 gives me 2. So the velocity vector for Kelly would be 3.464 headed to the right and 2 headed down. Now in order to show that this is down, I'm going to make that a negative there. So in order to calculate Kelly's momentum then, I have to take Kelly's mass, which is 15 kilograms, and I have to multiply it by this velocity vector, 3.464 comma negative 2. And if you're multiplying a vector by a scalar, right, something that doesn't have a direction, you just toss it into the brackets. So P would be 15 times 3.464, which gives me 3.464, 51.96. And Negative 2 times 15 would be negative 30. All right, so there's Kelly's momentum written as a vector. If you wanted to know the magnitude of that, so if I wanted to know how much momentum Kelly has, magnitude of momentum, that's just asking how big the hypotenuse of this thing is. Kelly's momentum vector is 51.96 this way and 30 in that direction. So I'm after this. How big is that momentum in total? Well, maybe you can see that this is just Pythagorean theorem. This squared plus this squared should equal this squared. So 51.96 squared plus 30 squared. I suppose technically that's negative 30 squared, but negative 30 squared is the same as 30 squared. Test that in your calculator if you're not sure. So 51.96 squared is 2699.8416. 30 squared is 900. It's 359.8416. And to finish, I need to square root that, which gives me 59.9986, which I'll round to 59.999. Now I have a feeling that if I had not rounded down here, this would have ended up as exactly 60. That is basically 60, depending on how many decimal points you want to take. What I've got here is Kelly's momentum written as a vector. It's this much horizontally, this much vertically, or it's this much in total with units kilograms meters per second, because it's mass times speed, so mass times speed. What is a kilogram meters per second? I don't know. It's not really a thing, right? It's not a unit that makes sense as an object. It's just sort of a construction so that we can carry them through in case we need them. We're going to clear this off and we're going to try a few more examples of two different masses, and then we're going to let those two masses run into each other and see what happens. All right, so we have two objects here. We have Anne and we have Kevin. Anne is 30 kilograms, Kevin is 40. And we're going to set Anne headed this way at 7 meters per second. So I could take Anne's velocity, write it as a vector. So the velocity vector for this would be 7 headed to the right, so that's positive 7, and 0 headed in the y direction. That means that Anne's momentum would be her mass multiplied by the velocity vector, which means she has 210,0 for her momentum. If I do the same for Kevin, I'm going to look at Kevin and I'm going to see that he's moving, let's say, 5 meters per second that way. Well, I can write Kevin's velocity vector then as 5, 0, and I'm going to make this 5 negative to show that Kevin is headed to the left. That means that Kevin's momentum vector would be 40, that's his mass, multiplied by this velocity vector. Therefore, the momentum Kevin is experiencing is negative 200, 0. All right. So that's pretty straightforward. You just get the momentum of each object that's involved. And now what I'm going to do here is let them slam into each other. And the mathematical thing that you need to understand about collisions is that the momentum that you had before the collision must match the momentum you have at the end. So just like energy needing to be conserved and matter needs to be conserved, momentum needs to be conserved as well. So if I just jot that up there, momentum before the collision has to equal the momentum after. So in order to get the momentum before, I'm going to look at the momentum that Anne had when we started and the momentum that Kevin had when we started. So that would be 210, 0 plus negative 200, 0. And that has to match the momentum I have after the collision. 210 and a negative 200 gives me 10, 0 plus 0 is 0. So there we go. So we have to ask ourselves a question before we can proceed with this. And that question is, what does this look like when we're done? So the first type of collision we're going to do is called a perfectly inelastic collision. Perfectly inelastic. And what that means is that the two objects leave the collision stuck together, so that they've left as a single object. Leave as a single object. Okay, so this is the before picture. Before. The after picture is a giant ball with all these letters in it, right? Like and Kevin. So they have fused together into a single object. That means that this massive object has a mass of 30 kilograms plus 40 kilograms. It's a total of 70 kilograms. So if I try and do the momentum afterwards, that means I have the mass after multiplied by the velocity vector after. So 10, 0 is 70 multiplied by the velocity vector. Divide both sides by 70. So my velocity vector ends up being 10 divided by 70, which is 0.143. And 0 divided by 70 is 0. So what I've just figured out is this fused object is traveling at 0.143 meters per second to the right. And 0 up and down. So when I took these two objects, if I let them strike each other under perfectly inelastic conditions, that means that these two objects fuse completely into a single object, I can reasonably easily figure out where that fused object was going. And if you look at the results here, Kevin is heavier than Anne, so you would think that Kevin should be able to overpower Anne in a collision. But Anne is going faster. So if you consider those two variables, the fact that Kevin is heavier but Anne is faster, and you let them actually strike each other and conserve momentum, it turns out that Anne's speed advantage manages to overwhelm Kevin's mass advantage, so that the object that leaves the collision has a net velocity this way, in the same direction that Anne was headed. And not only do we have the fact that it's going to the right, but we have exactly the velocity that they will be headed at.